Hello there, I'm Greg Watson, and we're going to be kicking off this QUALCON APQO 2021 conference on the theme, The Quality is Now. I'd like to open by discussing this topic, digitalization, stimulus for reassessment, rethinking, refinement, or revolution of the quality profession. We're being faced with a lot of changes happening these days, and the question that we have to ask is, how do we get ourselves ready for it? What are the things we need to do? So what I'd like to do as we discuss this today is, first of all, set up the situation so we have a clear understanding of what's going on. And then we'll come around and sort of dissect what we really mean by some of these technologies that maybe seem mysterious to some of you that haven't been following them. And so we want to sort of eliminate the mysteries around them. And then finally, we're going to end up with what sort of recommendations can we make about how we prepare ourselves and how much sort of new learning we need to get into to be able to accommodate these changes that are being, if you will, instilled upon the quality community by a technology community that's being driven because of this Industrial Revolution 4.0, which began back approximately 12 years ago with an effort by the German government. So let's begin by thinking about this. I'd like to start with a quotation here from Clayton Christensen, who passed away recently, but he was a professor at Harvard University, and he'd written a number of books, The Innovator's Dilemma, The Innovator's Solution, DNA of Innovation. And what he has talked about throughout his career is the idea of disruption. And what I understand today is, as I look at things, we are living in a disruptive age. And out of this age, we have coined an expression called Quality 4.0, which is sort of a response in general to say, hey, what is quality going to do as we face this new digital age? And Christensen made this observation. He says the reason why it's so difficult for existing firms to capitalize on disruptive innovations like digitalization, big data, and so forth, is that their processes and business model that made them good at their existing business actually make them bad at competing for the disruption. So in other words, what led to success in the past will not lead to success in the future. So what is digitalization? Well, it's influenced many of the technologies around us, and it's enabled a significant shift in the way we think about things. And it's used as a means, if you will, to discuss what we talk about smart systems or enabling smart technologies. You may have heard of smart homes or smart cities or smart cars. You may be driving a car that has more intellect than we do. And so as we start taking a look at this, we start seeing digitalization is happening everywhere. And it's being integrated into our lives in faster and faster pace of acceleration. So digitalization is enabled distributed sensors to collect real-time data, transmit it to some massive storage system which exists in the internet, a place called the cloud, which makes it accessible for multiple applications that are able to source the data for hidden relationships that enable them to build new perspectives about what we observe and new knowledge about how this information integrates into something we did not perceive before. So digital systems enable computing to perform tasks that 20 years ago only humans could do. And it's been demonstrated to pass human capability in several logical tests, which are enabled by what we call self-learning, which is an application of what we call artificial intelligence. And if we take a look at this, we see that there are a number of these digital technologies that are influencing quality today. Now, there are literally a plethora of applications of digital technologies. However, not all of them are equally reliable, or are they actually really applicable for all operational situations. This is a world of caveat emptor. Buyer beware. Look out for what you're buying. Be really certain that this application does fit your need, because there are so many different choices of technologies, and within each of those technologies there are many different offerings, whether we're talking about artificial intelligence, machine learning, data filtering, neural networks, blockchain, adaptive feedback, remote monitoring, robotic control, or document control. All of these technologies offer different things. But the question every organization has to ask is, who will serve as a neutral arbitrator judging the value, appropriateness, and effectiveness for the proposed digital methods. And this is, I propose, a job that quality professionals can indeed step up to. So let's introduce the technology. First, let's talk about artificial intelligence. In its simplest definition, artificial intelligence, or AI as it's more commonly known, is a computer-aided system thinking. And it's doing things that humans can do. AI is a field that combines computer science, robust data sets, and digital technologies to enable problem solving. It has some subfields of machine learning and deep learning that enable many of the advanced systems that are in use today to develop more rapidly and be introduced in systems by mimicking human action and learning based on examples that are captured by monitoring real-time data streams and observing patterns that lead to successful outcomes as compared to those that require rework by humans or reprocessing of information. So we can get it right the first time, many times with this. Machine learning is a second technology. It's actually a branch of artificial intelligence. It uses the data to enable machines to learn to perform tasks through a process of self-instruction. So it examines databases, learns about things that it observes made successful states or unsuccessful states as it's taught. So this technology is evident in many prediction schemes that we see used today. So recommendation schemes of marketers, like in Amazon when you get books recommended, or the self-driving automobiles that tell the car how to perform given the states of the sensors that are reporting to its central mind about what's going on around it. Virtual assistants, like Siri, for instance, that's giving you advice about things as the agent Siri is capturing information about your preferences, about what you like and don't like. Or facial recognition systems, where we see these being largely used in many countries today to understand who is doing what, or perhaps provide security for your phone or an internet or a banking account. And then email reply prediction applications. These are things marketers use to find out what sort of database do I need to be able to get the sort of sample I have to have for a particular survey or satisfaction type of instrument. Now these machines learn by self-observation. They use pattern recognition, or they may be taught using particular data sets that speed up the ability to make right choices. These are, if you will, instructional data sets where we know what's going on, and then the computer merely has to replicate what was going there, and then it learns the patterns that are underlying the ability to replicate those outcomes. We also may have experts serving to instruct in the process, and these experts are guiding, or they're teaching, if you will, the algorithm how to make right choices when given alternatives. A third type of technology that's applied can also be used in combination with AI and machine learning, and it's called data filtering. And this is a process of selecting a subset from a large database by stratifying it according to some logical factor, like demographics or timestamp in a series of actions. And it uses this to refine its organization of information by eliminating data that is considered redundant, repetitive, irrelevant, or perhaps even sensitive, such as personal identifications in a healthcare database. And it parses the data into rational subgroups. So this enables sorting according to importance for easier access and subsequent data queries. Data can also be edited or manipulated in this process. For instance, it's possible to filter data for noise cancellation, or developing probability distributions that describe performance over time. And this is what's called an optimal estimation filter, or a Kalman filter. It's also possible to apply tests for association or clustering to discover affinities that exist in the data. The next item is called neural networks. And I think this is something people have been familiar with because of science fiction. And we start seeing computers that supposedly act like humans. They become the computer brain, if you will. Now neural networks operate like the nodes and synapses of a human brain. And they transmit signals just like our nervous system does. In reality, they're just algorithms that recognize the underlying interrelationships in data as they move from different nodes, and they adapt to changing inputs and result in delivering the best possible result without needing to resign the output criteria. So we don't give up on the output criteria, we keep it. That's going to be stable, but we use the input criteria as a way of choosing what's the best path to get to that desired output criteria. Artificial neural networks are a subset of machine learning, and they enable what's called deep learning algorithms. And it has some learnable parameters to iterate across inputs and processes, inputs from different source nodes across the network. And it calculates losses, or the amount by which it's in error between the observed and the ideal state. If the artificial neural network is trained on known data that's delivered in a forward pass, like going from the beginning of the process to the end, we can create an inference. But the ANN also can use what's called backwards pass, or backward propagation. And here it calculates the error function, or if you will, blame for errors, and establishes a new learning weight for the system. What do we do in these sorts of circumstances based on what we've learned to get to these final states? And then each of these refinements with new data improves the capability of the artificial neural network to gain the solution state that we're actually seeking out. Another one's become very familiar to many people because of Bitcoin. It's called blockchain. Now, blockchain was first described in a paper, a theoretical paper by Stuart Haber and Scott Stornetta in 1991, as a system that used double timestamps to prevent it from being tampered with. So what this means is blockchain is actually a database that stores information in blocks, and these blocks are chained together. So as new information arrives, it's stored in a new block, and this is then chained to the old block, and they are located typically in decentralized servers. And so each node in that blockchain stores the entire history, and that enables self-correction because the blocks communicate with each other. So new blocks are stored linearly in chronological order, where the data is structured into chunks. Each block has a precise timestamp as it's added, and it contains a hash. Well, that's, if you will, a mathematical encryption code that identifies it as a unique place, and it also has the code of the block that precedes it in time. So this doubles up on the security of the blockchain system so that the data is very difficult, if not impossible, to tamper with by a hacker. And that's why it's being used in crypto security, but it can also be used in many other applications, such as in supply chains or process management of data. Another system is, once we get this information, we can have what's called adaptive feedback. And this is what's used in a control system. And so there are basically two different types of control systems that use feedback. One is a fixed control and the other is an adaptive control. So what's the difference? A fixed control system compares performance against reference data to the output that it makes. And it does this by determining what's the error that's applied, and then can we use this as a control signal to readjust the process operating parameters. This controller is basically deterministic in its operation. In other words, it's using a fixed formula. In an adaptive control system, the relationship between error and the control signal is not fixed, but it varies according to parameters of one or more variables in the system, and sometimes which variable is most important can change. So this type of controller is actually probabilistic in its operation. So it's suitable for many of the advanced algorithmic applications that we see once we digitize production systems. Another thing that comes into this technology is called remote monitoring. So there are a number of different ways this is used. So remote monitoring management is an ability to view production status, performance, and remote behavior so that we can use the Internet of Things linkage and cloud computing to track results. So this monitoring capability is performed by connecting some digital device located in a production process. So maybe we see a sensor that's detecting flow in a process, for instance, and it's located at a process control point. And the question is, should we open the valve and make it flow faster, or close it and make it flow smaller? And so we use these control points for managing applications and software, whether it's at a local level or at a global level in the cloud, and we can proactively monitor and diagnose real-time data flow that's captured from the networks. And we use devices like the flow meter that I just talked about, maybe a data probe, or specialized sensors like for temperature, pH, or other discretely available data sensors that we can actually capture digitally. So these systems enable early detection and response to defect data or critical situations, and they minimize the time to return the system to a state of control. So basically, we can almost in real time see what's happening and create systems that create the state that Walter Shewhart called maximum control. So no longer do we have to wait and capture lots of information through statistical process control charts, but we can actually reduce the time to manage corrective signal management. Another thing we see is robotic control. And this is used with the remote monitoring and the adaptive filters. And so we see that this is a process that applies digital signals about the state of performance to adjust the system the throughput characteristics. So all robotic control systems should enable human intervention at the control interface so that we can recover if there are any errors or abnormal events that happen in the process. What this does is it allows us to intervene in the process. And so human beings become, if you will, the final checkpoint for the quality of that throughput. So an integral part of this type of control system is collection of data using a statistical methodology to detect requirements for adjustment or actions that adjust the performance boundaries of the system that's being controlled. And these predictions can be based on statistical process control, optimal estimation algorithms like a Kalman filter, or a predictive model which uses a digital twin to determine the errors or such predictions may be based on statistical process control, optimal estimation algorithms like the Kalman filter, or a predictive model acting as a digital twin to determine the error state in the output data, where it's comparing, if you will, the ideal or noise-free model with the real-world model, which has noise in it. And that way we can cancel out the noise and readjust the process. Another area here is perhaps touching the base that many quality professionals understand, and this is document control. So one of the key elements in most fundamental quality management programs in organizations is the management and control of the documentation of that quality system for procedures, reports, and data. So automated document control manages critical technical documents in a way that's flexible and efficient, and it's aligned to the compliance needs that the organization has. So it manages information like policy, production procedures, product specifications, or product descriptions. So even position descriptions of people. It's an automated way to capture instructions, understand how to author new instructions, to digitize data, secure it in a system so it can't be tampered with, and this is in the authorized version of the documents. It can control revisions. It can also tag them with identifiers and also use to approve them for final application, as well as to manage important documents. If we couple this with something called natural language processing, an automated document control system can prepare the first draft of work procedures in what's normally is a difficult and time-consuming task, which also has a high risk of inducing human error and bias in the system. So the automated system can conduct its own process mapping audit to perform the procedure. And this is actually begun today in things like a program called Celanese, which actually does automated process mapping based on the data that's hidden in SAP. So what could be expected from digital control? Well, we see that there are some enabled digital system features. First, we control production flows. We enable the system for remote monitoring, diagnostics, and software upgrading. We can manage the system's data history. We can automate quality control and data collection, and also we can reduce headcount of people. Desired benefits, though, are reduced throughput cycle time, reduced variable costs, decreased time required for troubleshooting and diagnostics, increased uniformity of quality in parts and process data, and it enables first-time corrective action to problem situations. So we see that there are features that have actually very desirable benefits that management would be attracted to want to implement these technologies. But what we see is that this digital technology creates systematic disruption. So digital technology will change the way people work and how groups collaborate. So the result is worker redundancy. We have capability obsolescence and replacement of people by technology. So to facilitate digital transformation, we have to do some sort of management of skill and competence as a way to transition workers. This is called hitozukuri in Japanese. It's managing the development of people. And this is an essential item that it must not be avoided, it must be emphasized in any sort of transition to this new age of digital technologies. So equitable transformation of an organization in a Quality 4.0 world means that dignified and respectful career paths are developed for workers who are eliminated. So organizational culture must build trust to assure workers are treated with respect throughout this process. So cultural integrity must be displayed to workers, and executives must speak with clarity as their message stay in corporate memory. In other words, even the people who remain in the organization are affected by how the executives actually manage the transformation for those people who have to find new careers. So the way that management has in its actions displays its attitudes and its feelings about how they value the workers. So the human aspect of digital transformation is often much more significant than the technological change that it's accompanying. So what is the expected return on digitalization? So first of all, we expect increased productivity as improved flow control enhances product and process quality and reduces variable costs. Second, digital technology offers an opportunity to innovate in product and process design from market research to production and to include also customer relationship management. For instance, by using software as a service that then directly talks to the customers where they say directly what they want as a requirement into a system. We also see that selected digitalization can eliminate dirty, dangerous, or demeaning activities in daily management, which can improve the quality of life for workers by reducing safety hazards, increasing the controls related to privacy and security issues, and enhance the benefits in terms of health and welfare on the work environment. This also can shift work externally by engaging users or customers in self-service functions. So these are all important things to gain, but they are also met with what we might call unintended consequences. So we'll see little jobs will go away. If inspection can be audited, we don't need inspectors. If calibration can also be audited, we don't need calibrators. If diagnostic and corrective action from processes can also be audited, maybe we need less people who are actively engaged in those processes. Monitoring and auditing can be automated, so maybe we don't need to have as many inspectors and auditors. And data sampling can be automated, which means we don't have so many to need for so many people to go collect information to understand what's happening. Now, some people estimate that these jobs engage as much as 30% of the current tasks assigned to people working in quality today. So what will remain needs to be shaped into a new set of professional competencies that become elevated to the senior level, where the quality senior person, as quality manager, director, or executive in charge for quality, becomes an advisor to the top management, and they become a designer of performance systems that support the end-to-end business, not just introducing new technology. So this means quality will move from a strongly operational focus and start embracing more a strategic focus in the organization. So how do we manage this disruption? What can we do about it? Well, there's an ancient Oriental expression that comes from around 300 BC. I believe it was Confucius or Lao Tzu who first said it. Step by step, walk the 1,000-mile road. In other words, if you get a look and you say, I have 1,000 miles to go, you can get depressed. But if you take it one step at a time and logically move one foot in front of the other, you can get there to the end. But think about where I must go first and how I then move one foot in front of the other. So we have to use the strength of our process thinking and measurement knowledge to help guide this transition. Now, quality people are kind of unique. We are by nature astute observers of production systems. We're also purveyors of profound knowledge from measurements. So these capabilities are absolutely essential to successfully surviving digital transition in a company. And they provide a foundation for unique contribution of our profession during this disruptive period. So what we see is we have to understand what is the nature of a productive system. So according to Richard Young, a professor at Northwestern University, a productive system is a collection of if-then rules. Sounds like computer logic. That form an information processing computer simulation, well, it is a computer system, model of some cognitive task or range of tasks. And this includes what's called a digital twin. So according to him is everything that we're doing in a productive system can be converted into a digital image, which we call a digital twin. And productive systems include cognitive acts of learning and maturing to function properly. So this integration of things and people really characterizes what we're calling quality 4.0. And these productive systems will typically have 5 elements. So first, there's a hardware, software, technological production mechanism. This is the equipment, the robots, and the software that operates them. Second, we have human social systems, designing and executing the systems. So these are the people that create that system and the design for how it's going to come together and be used as a system. Third, we see management information systems and the knowledge base that performs the operations, including that human skill and competence of the people involved in the process. Fourth, we see data collected about how the system operated in the past and the activities and the feedback loops that are necessary to maintain control states. And so this is understanding about the flow of the system and how data, if you will, confesses how that flow is going so we can actually use the data to improve it in the future. And finally, we see its cultural values, style, and moral codes of working in groups. So how have we decided as a group of people in this organization, using our processes and these new technologies, how will we create the system of the future that we'd like to have? So, if that's a productive system, what can be the causes of disruptions? Well, we see we can have, first of all, interruptions in the flow of materials, parts, or assemblies. Or maybe there's poor communication of plans or production requirements. So don't really understand what the customers wanting. What are they really asking for? Or maybe it's incomplete, or it's contradictory. There can also be issues in production machinery or system software. Maybe we have the test version of software and not the final version, and it's got codes and errors in it. Or we're getting a piece of machinery that is being adapted but never actually used in exactly this application before. We can see shifts in customer demand, markets going up or down, or economic conditions, the availability of money or the constraint of monetary supplies. We can also see maybe we don't really have the right understanding of production status. We're not monitoring it in a timely way and reporting it so we can understand what's really happening right now. In other words, our data has a time lag and it's too late to be actionable. Sixth, we see there's an ineffective adaptation of new technologies or systems. We choose to adapt things without a plan, and that's a fundamental problem. So how do we choose what to do first, how to do it, and then what's the best way to introduce this in the future? And finally, there could be natural environmental occurrences or acts of nature. And so things like we see the the problems with rare earth supplies in the chain of materials, which is reducing today the availability of computer chips and batteries. So what can we actually do around these things? Well, we have to build what's called profound knowledge. And what is profound knowledge? Well, Deming identified a system of profound knowledge in his 1990 book called The New Economics. Now, he never defined profound knowledge, but in my doctoral dissertation, I defined that profound knowledge is a statistical understanding of the control of real-world process behavior so that future states can be predicted to some probability or to some degree of confidence. Now, there are 4 elements in Deming's system of profound knowledge. Now, he defined them rather curtly and didn't actually develop good definitions for them. But he called the first one appreciation of systems, but I think we need to go further. It's structure of systems. So understanding the system in which work is being done and the decisions are being made. That's about process design and process management. The second is statistical thinking about process variation. So this is profound knowledge of system outcome, which results from finding and controlling variation. And we know this as statistical thinking. Third, he said theory of knowledge, but we need more than theory. We need both mind and hand, which means action. So it's actually the development of knowledge. And we see that scientific knowledge comes by observing work, defining a theory, testing and confirming it, and acting on it, what we generally call plan, do, check, act. And finally, he just said psychology, but we actually care about the impact of psychology. And that is, human behavior has to be understood, interpreted, motivated, and coordinated to achieve results in a collaborative culture that's focused on humanity. So, digitalization is affecting quality greatly. And I go back in my history to the late 1980s. I was at Hewlett-Packard in the corporate quality office. And at that time, HP developed a model to understand the readiness to adapt new digital technologies in production. At that point in time, they were moving from through-hole technology and printed circuit board assembly to what's called the surface mount technology. And as the boards were getting more and more detailed or more dense with different types of parts, the question is, when are we ready to implement those new technologies? So they developed a process, and it's called UDSO, which is an acronym for 4 steps of understand, document, simplify, and optimize. And it uses a Japanese PDCA process to ratchet up performance using sequential improvements. So this systematic process standardizes work by engaging worker teams to raise their readiness to adopt new technologies in production systems. The first UDSO steps define standard work, while the final step adapts that technology to the streamlined production system. So the 4 steps of UDSO actually follow 2 steps that prepare for digitalization. The first 3 cycles, which is understand, document, and simplify, they develop a foundation that's called a daily management system. And then the second phase, which is talking about the automated digital cyber production system, or bringing in the technology. This is optimize or automation. And this is integrating the socio-technical aspects into the technology for a process that's already been established and streamlined without waste. So if we take a look at this approach, what we see is the steps go into understand, and so that is standardize, do, check, act. It's the same cycle. It's part of the Japanese daily management process. And so then we get to do, after we get out of this process, the document step, the standardize, do, check, act cycle here is a second cycle of the same activity. And now that we've understood it, now we can observe it and document it because we understand what we're documenting. Once we've documented, we then have a basis to create a simplified model. The simplified model removes waste, it removes losses, it removes friction that end up creating problems in that process. So when we've completed that third cycle, we've developed the standard work. So this is about business fundamentals. And here we've reached a maturity level where we can say we've actually now got the capability to have standardized work. And when we go to the 4th cycle, step 2, it's about system design. This is the optimization step. And this tells us that we have actually moved from the very beginning where we standardize, improve. Now we're transforming the process. And what we've demonstrated is that there is readiness for automation. So this approach seeks to understand the nature of work, to document standard work, and to simplify it for automation, which then follows that basic approach to establishing the daily management system. So in each of these steps, we see there's a description here. I'm not going to read these because it's something that you can read and study. But basically the first step is seek first to understand. And Taiichi Ohno says, go and see for yourselves. Figure out what's going on. So the first time we take a look, how does it flow? Where's the work constrained? Where is it yielding value? And we have to understand the as-is process first, not create a should-be, but just understand what's working and what's not, and why is it not working. That's understanding. The process of documenting is to understand the basically detecting and characterizing those process flows. What are the activities? Where are the decision points? Where are the measurement points, the control points that give us this deeper understanding of the system? And documentation does not have to start by being very heavy. Taiichi Ohno told the workers, don't begin too rigorously, but start and make room for improvement, because every time you do a cycle of improvement, he says, that's what Kaizen is. Keep it making it better, one small step at a time. But we see that productive systems are rules that define the control points, and this becomes then the basis for doing automation. The third step, simplify, is familiar because it embeds the same quality improvement methods we've used for decades, SDCA and PDCA. And then we move from SDCA once we understand the desired work discipline, and then we understand what can we do to make improvements once we integrate new technologies. And that's when we bring PDCA in. The big distinction that I make between SDCA and PDCA is that SDCA works with the standard process, it works within the budget of the standard operating system, and it works to eliminate the problems that people detect in the system that keeps it from operating at a maximized efficiency. Whereas PDCA is integrated with management's decision that we need to provide additional decision rights and capability and resources, because the system as currently designed needs a new design, if you will, to move things forward. When HP first developed this UDSO model, they had the intent to create a factory of the future. And there were, at that time, many organizations were implementing intensive robotization of their production operations. And this occurred during the late 1980s. At that time, General Motors had actually implemented an investment decision of $20 billion US dollars to robotize, if you will, or automate its manufacturing facilities for cars. And the problem was they were seeking, or their purpose or aim was to create a more productive output. However, the output that they created was not more productive. So it didn't become a reality. So the human component in the system was largely ignored because of the myopic approach to integrate robots into production system in order to replace people. Now you have to remember, at that time, the cost of production was only about, caused by human salaries, was only 10% or so of the total cost. And that was a very large investment to get people out of the system. But we see that this UDSO's final step requires forecasting technological elements and deciding on feasibility and cost effectiveness of those technologies, what should be included in engineering products, how do we design the interfaces and control systems, and how do we engage the humans and their intellect in this process. So I want to switch a little bit towards discussing a little bit about Quality 4.0. So this idea, Quality 4.0, was framed in 2017 to describe how a German strategy for industrialization called Industry 4.0 would influence the quality function in organizations. Now originally it referred to treatment of the massive amounts of data that would be available in real time and using it to automate feedback loops and maintain performance by using digital methods like artificial intelligence, machine learning, and robotics control. And what was actually in many German companies was the idea that quality would become a hygiene function, what Dr. Kano just called a must-be part of the system. And so that much of that function could be automated and thus eliminated. But now what we recognize is that Quality 4.0 is not a set of tools. It's not a set of methods. It's a disruptive transitional period when transformation is occurring to the technological, human, and cultural systems of production as a result of some chosen strategies for automation. It's not a particular set of methods and tools, but it's how each organization will transition to a new state of quality based on their investment decisions. Now we see quality professionals are uniquely qualified. This new state of quality actually elevates quality thinking from its constraints in operational activities to a level where it works as a generic strategy for continual improvement to benefit all of humanity, not just its own organization. So every technological evolution has brought with it a new language and new methods. And the digitalization of work is no exception. However, quality professionals have always thought and worked using algorithmic thinkings by applying data to seek problem solutions, which is the outcome of applying these exact same new digital technologies. As a result, the routine works are eliminated, but they will be substituted by a growing emphasis on what's being called macro quality. And this is elevating quality from just one firm into what are the implications of that firm's work for society and for the world as a whole in ways that benefit all of society and assure that there is no harmful effect on our biosphere. And so quality then is being elevated into a social system that affects all of the world and how organizations work together for the benefit of all mankind. So what enables readiness for digitalization? Well, readiness for transition to a digital ecosystem, if you will, requires three enabling activities. So first, we have to develop confidence. And how do we then insert this in system and statistical thinking in the organization so we understand the theoretical construct of business systems? So this competence instills profound knowledge of the end-to-end productive system and is a foundation for design of a digital system that can accelerate system performance. Developing an engaged workforce facilitates transformation by giving workers competence that's required for applying the new technologies and for transitioning legacy workers who've understood the old way of doing things in manual systems. So those workers are assured of their employment security and they gain trust in management's decisions about shared purpose. This means that they're given new value-adding opportunities. And then finally, developing a systematic implementation plan to sequence the digital technologies, maximize value for stakeholders, as well as for the employees who are going to be involved in these processes. So quality can actually step up and manage the transition projects. So disruption creates both problems and opportunities. Some of the new opportunities available to quality professionals include capitalizing on our knowledge of data and systems to design the new digital structure and its measurement and control characteristics. Maybe we can be serving as project managers for integrating digital technologies into productive system for operators, for operations, for diagnostics, for control and feedback to customers. Or maybe we act in a new role where quality is the differentiation strategy for the entire organization that requires broad knowledge of how the entire business system works as a collective whole. And finally, developing our capability to act as a trusted advisor in a role as an internal consultant to management in the senior levels for planning, diagnostics, and review of the system so we make sure that it goes in the right direction. Now, what can you do to prepare yourself? So here are some of my recommendations of areas for personal development. First, I think you need to learn how standard cost management really distorts the information senior managers use in their decision-making process and how to improve its quality. What we see in most, if you will, standard accounting methods is that there's a gross distortion of information. This is the same place where we get the idea that quality costs too much, even though nobody can point to what is actually costing more, because they're using outmoded models that say there's a trade-off between cost and quality. And while that may be true in some technology areas around parts or materials, that's not true in the overall process world in which we work. We also have to discover how these technology pieces fit together in an architecture that's appropriate for your organization's business model they would like to have in the future. We have to emphasize discovery of digital sensor technologies and measurement capability that could be applied in our system. And how will this information be integrated into a performance management system that gives us predictive analytics of future outcomes? Then we have to increase our own communication skills, maybe our negotiation capability, and ability to operate across the functional boundaries, informally working across that structure of your organization. And then finally, we have to seek to prove ourselves as trusted advisors to senior management. And we do this by leading projects, pilot projects, if you will, that start the journey and demonstrate the value that we can contribute to the end state. So quality professionals will need to help in the transition. As jobs are eliminated, people will need help because they don't understand what are their options or opportunities in the future. Only the service sector and industry is capable of absorbing the excess amount of workers that will be released from manufacturing organizations. And in the field, service quality is a core fundamental. So we see that the service organization will open up many opportunities for quality to be included. Displacement of jobs will also begin at the bottom of the education, experience, and vocational skill levels. And the people with these characteristics will be disproportionately affected. And that's actually problematic for many people who are in the older part of the workforce, because we have built careers on those technologies that basically can be eliminated by the new automated systems. And we also see that we can train people in how things work, because we can actually take an AI system and operate it in parallel, the digital twin. So it can not only be used for monitoring and corrective action, but it can also be used as a learning agent to teach or enable people to learn, trained, if you will, in how to improve in their critical and creative thinking skills, and then how to perform the jobs in combination with these technologies. So an AI agent can act as a digital mentor, if you will. So as it gets trained in the process, it can also adapt people. And so how can you learn as the computer learns? And it can show you, here are the new lessons that we need to take forward. So the challenge as we take a look at is, how will we as individuals adapt to this digital age? What will we do to think about how our capabilities can act in there? Now, the future of quality is now. These changes are happening so rapidly, it's unreal. Used to be that Moore's law said that we were having a digitalization happening every 2 years, and that was the half-life. So every 2 years we'd see that technology would increase in capability and costs would go reduce. But now what we're seeing is that artificial intelligence is actually moving faster in just 2 or years at 3.5 times the rate that the technology was for hardware. And so we start seeing that this artificial intelligence age is actually creating major changes as the machines learn faster than we do. So what that means, there's a new imperative. The time is now. You have to invest in yourself. You have to think through the situation. What do you want in your career? How will you develop your plan to move ahead in the coming decade? Because the next 5 years in this decade will probably have more change in it than we've experienced over the last 20. So enjoy the conference. Think about it. Save some time for reflection. I know it's remote, but what that means is that you've got more time to think and figure out, what will this mean for your career development plans? I wish you all well. Thank you for listening.